Good afternoon, everyone, and thanks for joining us today. I'm Naveen Chandrasekharan, and I'm the Client Engagement Facilitator for the ANFF New South Wales node. Today we're going to be talking about the capabilities at UTS Hub, and predominantly Blake would be taking over from here on, but Blake is the technical coordinator for ANFF Hub since 2020, as he just mentioned. Blake's taken up his postgraduate studies at UTS with a specific focus on diamond fabrication methods and development of fabrication of diamond membranes. And he's right now, as he mentioned, he's coming out of the disruptions and trying to promote the facilities at UTS. And he's going to be talking more into that. But for those of you who don't know what ANFF is, it's can I go to that slide? ANFF is basically a network of research infrastructure that helps researchers and industry members to take their idea to prototype into commercialization. So we help with managing resources associated with technical expertise and accessing research infrastructure for various stakeholders that are willing to explore the areas in nanotechnology and various applications associated with it. So I think I wouldn't take much of the time, but just wanted to get introduced to you all. And if there's any questions or if you wanted to engage with us later on, just feel free to, we'll share our contact details later on. And we'll open the floor to questions towards the end of the session. But for now, I'll pass it on over to Blake, who can take on from here and share what capabilities he's got at UTS.
Well, hello, everyone. So as mentioned, I'm Blake. I am the technical coordinator here at UTS's Optofab Hub. Now, predominantly, I'm based at UTS. So a lot of people should already know UTS. It's one of the most central universities across Sydney. I've recently went about I was going to put up a nice image of the famous single tower, the building one, the one that looks like a giant Lego brick, but unfortunately, all the UTS advertisements started putting our new fancy building 2 up the front. So we don't get quite the pride of having I believe it was voted Sydney's ugliest building. So most people recognize UTS by that, but for the time being, we now have a fancy new building, which we hide behind. So like I said, UTS is one of the most centralized campuses across Sydney area. We're about a 5-minute walk from USyd, just up one street, 15-minute drive for UNSW, or 25 minutes if you're catching public transport. And we're very close to Central Station as well, about a 5-minute walk, which I timed a lot during my PhD here. So in terms of being able to get access to our laboratory, I don't believe there's going to be an easier university to get to. We are, like I said, directed immediately at Central Station, and we're not that hard to find after the fact, thanks to our ginormous and very ugly building. So we are located, the ANFF Hub, inside Building 7, which is a building that was built, I think, in the last 5 or 6 years when it was finally established. It is the new science building, and we are situated in the basement at level 0. You'll find us in this image. We are a nice curved front building in front of the alumni green, just housed behind the big central UTS tower. Whenever someone wants to come here, usually I'll just find them outside on the alumni green and then take them down to our laboratories, which are well hidden in Building 7's level 0 or in Building 4's level 2 in the MAU for cathodoluminescence. If someone wanted to come to UTS, they might want to know exactly what we do. And we are a part of the Optofab node. So that's the node that's associated with other groups like Macquarie and Adelaide, where we focus mostly on the fabrication and generation of optical materials, with a specific focus on processes like laser micromachining, functional optical materials. My particular focus is on diamond, although that's not our limit here. We also do things like photolithography and laser inscription and things such as, just to keep a wide variety of capabilities available to us here in our Optofab node. The UTS is the newest member. So like I said, we were only established about 3 years ago. And while and I recommend going onto the Optofab node to have a look around on their website to see what other capabilities we have at other universities. That website will be an ongoing updated process, and we'll be able to include all the things that I'm going to introduce to us here today. The capabilities that I have at UTS focus predominantly on the etching and deposition of optically active materials, with my particular focus and expertise being on diamond, although I'm pretty well established with a number of the other prominent photonically active materials. We also have cathodoluminescence. So to those of us who've been around in this industry for a while, UTS is one of our main scientific draws. Way back in the day was I believe we had the only CL system in the Southern Hemisphere at one point, and all that expertise from all those years of postdocs and PhDs being generated from this area in CL has stayed with us. And we try and keep that heritage alive within our ANFF hub so that we can bring it to the outer community. So we'll first go into etching. So the two etching systems that we have that are available on the ANFF hub, we have active right now the Intelvac NanoQuest, which is an ion beam etching system. And we will be having in the near future the Trion ICP RE, which most notably is going to have chlorine gas built into it, which is one of the leading things to have available to us when talking about nanofabrication capabilities. But first, before we get into the Trion system, let's talk a little bit more about the Intelvac system. So we have ion beam etching system, and it does have the capability of chemically active ion beam etching system. This system also comes with a load-locked omnidirectional stage, which means that you can do any amount of tilted etching samples and going forward and backwards, and also rotating the sample. This allows processes such as undercutting of, well, if I use my own research as an example, photonic nanostructures, but also allows other areas such as tilted gratings, including some metasurface materials, as associated with the secondary group here that we have at UTS, the TMOS group. We do have access to argon, which is the predominant, if you go through anywhere in the literature on ion beam etching, you're going to track down argon-based etching, especially for silicon structures. But we also have access to oxygen and SF6. The primary reasons is there are the occasions where you'll want to have a good or better mask selectivity between your different, if you're attempting to generate structures. And occasionally, depending on your substrate, you do need to have a chemical selective part of the etching mechanism, which will allow the masks to have different levels of effectiveness when generating nanostructures. A good example of that is the use of oxygen, which oxygen is used for diamonds. These are some of our first tests where we were just testing with a basic SiO2 mask on a diamond substrate. And we can see that with this use of an oxygen etching mechanism, we can have nearly pristine etching of the diamond surface and a near direct translation of the SiO2 mask onto the sidewall. Unfortunately, in this case, the mask itself was a bit of a rush job, so it's not as pristine perfect as we can make it. But it does show a nice translation of roughness of the mask directly into roughness on the sidewall, which then also shows that the etching mechanism has very little effect on the SiO2 and a lot of effect on the diamond substrate. So that was a nice little demonstration of the selectivity that can be granted through chemical etching. We do also have a SIMS detector, which allows us to do endpoint detection, as well as a very low amount of chemical analysis. So we'll be able to tell you what ions are coming out of there. You can take out of that information a ratio, but it is dependent on the ratio of the detector sensitivity. So mostly that's going to be used for endpoint detection. So what I mean by that is if you have multi-layer materials, a good example being aluminium, silicon, aluminium, silicon, aluminium, silicon, you'll be able to not only detect when you cut through those layers, but it'll be able to end the current process and also start a new one. So if you had to etch multi-layer materials with different etch chemistries or etch conditions, you can program this all in, which will be incredibly effective, especially for projects that focus on large scale fabrication and ongoing processes. So we have a lot of desire within this hub to have project-based capabilities come into us so that people can spend time, develop a process that's unique to their desires and needs, and then be able to essentially create that into a repeatable process where they can generate whatever structures they want. As I mentioned in the words there below, it is also programmable to have multi-step processes which does include different levels of access, where either at the lowest level, you can simply have access to predefined recipes where you can just use the system, put in your sample, press play and pull it out, and you'll have an etch sample. As you go higher and higher in the usage requirements and your training, you'll be able to then also generate your own procedures, save them to the computer, and come back over and over and repeat the process as much as you need. In terms of repeatability, I've included in here, this is some of our initial testing when we were determining the roughness of the etch over a wide scale. This is a silicon dioxide substrate, and as you can see, over the area of 6 centimeters, centering on the middle, this is all done with ellipsometry measurement. We found that the roughness of the etch across the substrate was only 1 nanometer or ½ nanometer plus minus. So in terms of etching accuracy, that is, I was personally quite impressed by it, but I'd like to be able to impart that etching quality off to you guys as well. So our next area that I'd like to talk about is the chlorine etching. Now this is coming soon to UTS, and by coming soon, I mean I convinced the deanery to sign this off within 1 week of wanting it. And I then convinced them to do all the paperwork, and they should be signing under the dotted line on Thursday, which means the machine should be here in a matter of weeks. We're going to get our system from Trion. We've used Trion before, and they've been quite useful. We have one SF6-based etcher, which isn't a part of our hub, but it's still one that I'm happy to use on our hub's behalf. And this one will be the chlorine-capable one. So to those of us who are familiar in the semiconductor industry, there are 2 reasons to want chlorine in your etching. Number 1 is for the etching of metals, and number 2 is for the reduction in the effect of micromasking from metallic contamination on the surface. A fairly famous example, at least in my field, was the use of Faraday cages for angled etching, where the introduction of chlorine reduced the effect of micromasking based on its ability to etch away that small amount of aluminium which comes off the surface. The target dates for this to be active for the community is around June and July. I'll try and keep the general community updated as it all comes in. Ideally, if all the stars align, that'll be the dates that I expect this to be up and running for the community. And it also should not be too difficult to get that prepared and ready to go for people to come in and use. Again, just like with the ion beam etcher, we'd like this to be used as a more project-oriented structure. So if you have the desire to get in there, create samples over a long period of time, or develop processes for your particular needs in fabrication, that's the kind of project we're most happy to accommodate for. I am also personally quite happy to just bring in anyone's individual samples if they need a one-off etch. We'll develop that as we go. In terms of what our etching capabilities have been, my specific area of expertise is in diamond fabrication, as I've mentioned a couple of times. That is not to say I haven't had a chance to do fabrication in other structures such as silicon carbide, and HBN. The 2 images I've provided here are the right-hand side being a single crystal diamond I bought from Element 6, and then etch that down just to demonstrate a pillar-like structure using an RAE. And the image on the left is a photonic crystal made out of a freestanding diamond membrane, which we made to demonstrate our capabilities in photonic fabrication, with the structure sizes of those holes being about the range of 10 nanometers. Now, moving away from our etching side of things, we now also have the deposition hand of our little hub, where we have 3 major areas of deposition. The first one being, as I've mentioned so many times already, diamond fabrication. So bringing in the SECI reactor that originally came from Macquarie University, we're able to do the overgrowth of single crystal diamond. Now, what this means is that we can take a small amount of diamond that is already predetermined. My particular area was in diamond membranes, but we can also do bulk diamond and nano diamonds, and we can grow this material outwards to make it larger. Now, you could do this for a number of reasons. The first one being is either A, you want fresh diamond. So your diamond could go through a number of fabrication steps if you're doing anything else to it, which can create damage in a top layer of diamond. The CVD overgrowth process is proven to recover the diamond surface, and the new material does not translate any previous stress, strain, or roughness that's imparted on the previous layer, unless that roughness is so over the top that you'll grow polycrystalline just based on different facets. But in terms of things like, I know a lot of groups do work such as ion implantation, this can recover that damage quite easily. The second area that distinguishes my diamond capabilities with the diamond capabilities found down in Melbourne is color center incorporation with a specific focus on group 4 elements. To those of us who are familiar with diamond color centers and diamond photonics, I'm sure this is all old news, but in case anyone here doesn't quite know this area, diamond received most of its very current research focus based on its potential in photonics, where it's found to have because it is a wide bandgap semiconductor with a 0 spin ground state, it has the capability of hosting optically active single photon emitting color centers. The most famous one being the NV center, which is also proven to be a room temperature spin controllable emission. I focus on group 4 emission, which has a number of benefits that are outside NV's capabilities, which include a narrow band room temperature emission, which then also has the capabilities of being ultra stable and having a number of applications, including thermometry and magnetometry. Beyond the growth of simply diamond, a number of users have actually started using the SECI microwave plasma CVD as a hydrogen termination tool, where predominantly it's being used just with other non-diamond samples. And because in all my scientific training, I'd had ample access to this CVD reactor, I wasn't aware how difficult it was to get your hands on a high power hydrogen plasma. So a lot of users have actually come in with the simple desire of putting a hydrogen terminated layer on the outside of their sample for whatever erroneous process they have. So long as your sample won't cause undue contamination to the chamber that would negatively impact our diamond growth, I'm quite happy just to allow people to come in and open up the use of this hydrogen for other non-diamond related purposes. And as much as I detail my growth to stand away from polycrystalline diamond, I am perfectly capable of creating polycrystalline diamond films, which we've done for projects, including one with Switzerland, where we just simply needed to coat and seal the end of a capillary tube with the use of diamond as an inert material that was also quite strong and resistant. Beyond the SECI CVD, we have the lebec 1500. Now this is not as technical area, but it is a tube furnace, which unlike a number of other tube furnaces has the capability of going up to 1500 degrees. This is because it's built out of predominantly ceramic components, which is what distinguishes it from your typical tube furnace, which only goes up to approximately 1200. This one, I would again love the availability of long-term booking projects. It has a very long ramp time of about 5 degrees per minute, I believe it is, which means you'll be spending a number of hours just letting it ramp up, getting to heat, running for as long as you can, and then the same amount of lead time going downwards. This is also a chamber that has access to vacuum compatible systems for if you need to do either annealing in a vacuum or annealing in a specialized environment, where we do have a gas controlled line which can go into the chamber, which would allow you to introduce inert gases such as argon or other specialty gases on a case-by-case basis. Again, this one is going to be pretty much open use for anyone who needs to use whatever project. The only stipulation to this is that if your project requires components that are unduly contaminated, then we'll simply need to purchase your own ceramic tube. So the only thing that you're going to damage is your own equipment rather than the general equipment which can be used. Our final capability in terms of deposition is the STF 1200, which is just another tube furnace. However, this one we've specialized in the growth of optically active hexagonal boron nitride. To those of us who aren't familiar with hexagonal boron nitride, it's a two-dimensional material with a range of emission properties depending on the kind of emitter that's grown into it. One of our previous PhD students developed a process where he was able to generate HBN with a consistent narrowband emission of a single photon emitting structure. So it had a G2 of less than 0.5. We've taken this and we've developed it into what would now be a tube furnace that's specifically designed to undertake the growth of a product. So we would like to, in the future, be able to grow this HBN, deposit it onto a substrate of the dealer's choice, and then send that out to people and sell it as a product. So while we are open to the concept of having projects that are given to us that would interfere with this growth process, especially if someone has a very long-term project, but otherwise this one we mostly use for the generation of a product which we would sell. And so if you ever need HBN, I know the old PhD student Noah Mendelsohn who developed this process used to go around to conferences with a little box full of his HBN that he used to hand out with his business card, because it was quite a useful product, especially when thinking about generating larger scale devices. So these are the three images of the three different growing and the three different deposition tools that we have, the left being the CVD, the lebec 1500, and the STF 1200 on the right, all based in our vacuum technology lab, which is one of the reasons why this product, this talk had the title in it of it working in a shed, as our vac tech lab looks basically like your average shed. I just figured I'd include some images of our deposition of diamond. On the top left-hand side, you see the growth of single crystal nano diamonds. Now, these ones were specifically grown to include SIV, and I've shown the ZPL, or the emission spectrum of the SIV nano emitters, which is around about at 740 nanometers. I've also included an image of diamond membranes. Now, diamond membranes was the particular area focus of my PhD, where I focused on the growth of diamond membranes and the fabrication of diamond membranes into photonic structures. This one happened to include the GeV, which is another useful emission color center, but the diamond membrane is also unique that it is a thinned, the one you're seeing there is only 300 nanometers thick, platform of diamond, which can be integrated into larger photonic circuitry, including being fabricated into structures before transfer, which is one of the last papers I published before I took up this job. So we can do the overgrowth of single crystal diamond, we can do color center incorporation, we can create polycrystalline diamond films, and we can do hydrogen termination with the Secchi microwave plasma CVD. In terms of our HBN, I included the figure from the paper of our PhD student Noah, which showed the nice thin emission spectrum, the 86% rate of always hitting near the 580 nanometer range of emission, and of course a G2 of less than 0.5, which to those of you familiar with the photonics community, anything less than 0.5 is considered a single photon emitter. Now, the HBN samples are grown with these flakes en masse, so when we give you a sample, you're likely to have hundreds per sample rather than one or two. Now, one of the topics that is also a part of our hub is cathodoluminescence, which is the process of using an SEM to interrogate a photonically active material with its electron beam, which then causes excitation in the sample and emission. What the Delmic SECOM CL system does is it is able to collect all that information and do spectral analysis on it. I will admit right now that CL was never a part of my major training, so it's probably the subject I'm weakest on, but I've got a number of experts around me who will be able to help out and have always been willing to talk to me about how to improve other people's projects as they've come in. Now, this tool is actually very powerful in the sense that you can take an SEM image and you can do confocal analysis across the entire SEM image without the requirement of refining it. You simply have the SEM image and you do your spectral analysis across that image itself. And as a full information package, it is capable of having an individually taken and saved spectra for every single pixel along that map. So if you were absolutely certain that you needed to know every single spectral detail about a specific sample, the image given here is one of HBN, you would be able to take that spectrum and know everything about it and create whatever figures or data you needed for your paper coming up. This has also been quite useful and is currently a project that's being undertaken right now in investigating photonic structures, where you're able to have a generated image or like a heat map of the structure at the nanoscale, which would allow you to estimate properties such as the light confinement or the EM or the TE or TM like modes within a photonic structure. This is quite powerful as it allows you to correlate the expected electromagnetic field around your cavity with an actual image. So you can do a direct comparison of your modeled cavity and your final fabricated cavity. So it is a very powerful tool. The only stipulation against it is that there are only some samples that can undergo CL, and that would require a discussion beforehand before we do any booking to ensure that you're not coming in and just looking at something randomly and not understanding why you're not getting any data. So the focus areas of our group and our particular area of expertise, for me, it comes down to diamond membranes, and I do diamond nanofabrication. Within our group, we do HBN synthesis, and we do photonic structure fabrication. We can also do small sample handling. We can do dry etching of nearly any material, so long as we're given the ample time to figure out the correct process for it. And of course, we can do, with our CL system, characterization of the tools. One of the fun parts about our particular ANFF hub is that I will be the main point of contact for anything you need to do here. In fact, I will be the only point of contact for most of the work you actually do in the area. And because I am familiar with not only all our ANFF equipment, but all the equipment that sits outside ANFF, I'm also happy in the right circumstance to go in there and do any extra little bit of characterization, a little bit of tooling, or whatever else is needed to help ease the project to its successful conclusion. When it comes to things like fabrication of structures, we do expect there to be a time frame which we can work out and develop the process together as a team. In discussion of small sample handling, I've done a few projects, one specific with UNSW, where I was simply capable of holding those. They had needed diamond membranes being handled and cleaned, which I was more than happy to do that for. Most people work with diamond plates, which are the scale of almost 0.5 millimeter, whereas I'm used to working with samples by hand that are about 50 micron. The image at the top right is actually a 50 micron membrane targeted to a 5 micron area. And we did all of that by hand. The area that it's sitting on is also a very thin membrane of silicon, so we also couldn't press down too hard or we'd have cracked it. So we're quite capable with our hands as well as our understanding. In terms of our team, our ANFF hub director is Igor Aronovich. He has a focus in photonics, wide bandgap materials, quantum optics, and his fearless leadership. We also have Mika Fam, who is our current research associate. He's with us for a short amount of time. He was there predominantly to help me in developing processes, because otherwise I am the only ANFF employee at this hub. So every other thing that needs to be done goes through me. He focuses mostly on 2D material synthesis, including a number of publications in the fabrication of HBM and diamond. But his main field of interest is he is a biochemist, and he is basically my go-to jack of all trades of every area of science that I might need some advice with. And the final team member is myself. I'm the technical coordinator of this hub. I am also the only ANFF employee of this hub. So that means, as well as doing all the machine repairs, fabrication process development, I also do the finances, and I am the primary point of contact for almost everything you need. The disadvantage being is that I am technically limited by manpower, so which means that you might need to give me a few minutes to respond back to you in case I'm caught up doing other things. But the benefit of that is that I am the only person that you need to contact when discussing directly with the ANFF hub. My area of expertise is in specifically diamond photonics, diamond fabrication, and nanofabrication, as well as technical support, and I have a fairly robust understanding of most common nanofabrication processes. I'm always happy to respond to emails and have a discussion, even if it winds up not being something that you could do directly with my hub, and even if I can just point you in the direction of a hub that's more suited to fulfill your needs. You can contact me, Blake Regan at uts.edu.au. We've included Navin's, all his contact details, because he is also going to be assisting with contacting me and helping distribute work where it's most needed. Like I said before, our hub, because of the way it's structured, we love large projects, ongoing, someone who I can induct, who I can train, who I can bring into the fold with our little group here. And then I will always be around to help you and assist you and make sure you're getting the best outcomes for your projects. However, you would also then have free reign to come in at your leisure, in your time, book the equipment and do your experiments. I'm here 9 to 5 every day, so don't be afraid to come and find me. And otherwise, I would like to thank you all for all your time coming in and listening to this little workshop that we had here, introducing the UTS hub and all our capabilities. And I've included on here, again, my email account in case you ever needed to try and track me down. Feel free to take it down there. And Navin's has been included down there. So to all the people and participants here, you now have my direct contact details. Please use that very wisely. And otherwise, thank you all for listening. I'm happy to answer any questions.
Okay, I have a question. Thank you, Blake, for your presentation.
Thank you.
On one of your slides, you introduced photonic crystal with a freestanding diamond columns. Yep. Yeah, I was wondering if it's possible to establish some collaboration. We need these samples for our honors project at ANU.
Absolutely.
Yeah. So, like,
how many do you need? I've got 2 on my desk right now.
Yeah. Okay. All right. Yeah. So.
Yeah. So that's a process I developed as the final project of my PhD, where I'm able to create 2D or 1D photonic crystal structures on a diamond membrane. That diamond membrane I specifically developed to not be strapped down to a substrate at all, which means I have demonstrated the pickup by hand and placement of these already prefabricated cavities, both 1D and 2D, onto different substrates. So that means that I am technically capable of generating a 2D or 1D photonic crystal cavity here in the lab, and then you'd simply need to come here with your predestined substrate or photonic circuitry, and I'll happily transfer that across. We'd need to probably discuss like the details more closely so that we know that we're on the same page with our fabrication and our time frame. If you need something that's very specifically built, all we'll do is discuss together and get the parameters and get the scale and get the size. Basically, let's map it out in 2D, and then we can take the fabrication from there. Okay, I'm also happy if you want to send that student here and I can teach them how to do it.
Yeah, that would be also another point. Yeah. Okay. Yeah. So the project starts like in June. So I contact you within the next couple of weeks.
Absolutely. Yeah. So my time frame up to June will be mostly dedicated to making sure our chlorine systems are all up to date and all put together and all nicely ready for the community to use. Otherwise, I'm happy to back and forth and to get a lot of specific details in the fabrication process. So if you bring it, if your student wants to learn how to do it as well and get like on the deck training, happy to take them in as well.
Okay. Yeah. Sounds cool.
Awesome. Okay. No problem.
Yeah, thanks, Blake, for the nice presentation. I had a question about this incorporation of the defect center in diamond.
Yep.
I understand you're working with the group 4 vacancies, but you mentioned briefly about NV centers as well. Is that a possibility there, or that is not developed in process?
It is absolutely a possibility. In fact, I spend a lot of my time trying not to incorporate NV centers. So all I do is basically not pump down my chamber quite as nicely, and you'll have NV centers. They are fabulously easy to make and robustly difficult to not make. So if you ever needed NV centers, I'm also quite happy to let you in and show you how to fabricate them. It would probably take you 1 day to get them.
Awesome. And like with these NV centers, are we?
Are you paused, or is that me?
No, it's not just you.
Okay. So I think you dropped out.
Or singles.
Oh, there you are. You're back.
Yeah, sorry. Yeah. So my question was like, is it possible to get NVs as singles, or is it mostly ensembles there?
So when it comes to CVD diamond, you're generally going to be having a difficult time getting singles out of the process, especially when it comes to NV centers. In CVD growth, you're mostly looking at having a uniform distribution of ensemble emitters across a full platform. Now, there have been techniques that are developed, such as delta doping, which can achieve a very low concentration of dopants, which then has the higher probability of introducing single photon emitters. However, if you're actually aiming to get single photon emitters, I recommend either, depending on your application, working with nanodiamonds, where you can delta dope them a lot more appropriately because you'll have a much smaller volume that you're trying to work with, or ion implantation, which I believe is a capability that our ANU hub might have. I know that's where I've sent things. I'm just not sure whether or not that's associated with ANFF. So it is possible, and delta doping is an established process. CVD mostly focuses on generating high density of emitters. So when it comes to projects that include applications such as sensing, you want to have a high density uniform emission so that you can do your sensing as an average measurement on an area, which increases the accuracy of the outcome. So rather than having one emitter, which can have variability of a certain percentage depending on the emitter, you'll have 100 million that you can average out and get a true reading. If you wanted to spend time developing the delta doping process, in theory, it's quite easy. So the outcome, the process of delta doping is rather than growing your system directly, you vent out. So in terms of NV centers, it becomes a little bit harder, but not impossible. You vent out all the nitrogen from the chamber, and then you begin the growth process, and then you spit in small amounts of nitrogen to essentially dope 1 nanometer layers with nitrogen during the growth process. And then when you go back and do your confocal analysis, if any nitrogen has been introduced, it'll only be in these very small layers, which reduces the probability of it being an ensemble. However, if you're serious about getting a lot of highly precise single photon emitting centers, I always recommend doing implantation method. Your only drawback to the implantation method is that the process of implantation damages the diamond, which means the overall quality of your emitters is reduced. But depending on your application, you might not care about the quality of emission, merely that it's single photon. So it, as with all fabrication, there's a trade in whatever direction you take.
Awesome, thanks. One last question. I do have several more, but I'll reach out to you offline. But one more question is about the dopant layers, right? Like, are there possibility of incorporating doping in diamond, like boron or phosphorus or other types of doping?
Yep. So boron diamond is a fairly established technique. The only reason I haven't done any focus on boron diamond with our hub is that I know the Melbourne hub does that already. They're pre-established to dope with boron. The process of doping with boron is just introducing a different boron carrier gas into the chamber, which is fairly doable. The only reason, like I said, why we haven't done a focus on that is because I didn't feel the need to step on Melbourne's toes in that one. So they're fairly well established as being able to pull off boron doping. Otherwise, the doped layers, when it comes to group 4 emission, just comes down to what you're introducing to the chamber during the growth process. And you can do that doping as an average across a full growth, or you can do it as a depreciation across the growth. And we can also overgrow the membrane with the new layer and then flip it over by hand and etch away the old material. So all you're left with is a doped layer. So there's a number of different ways you can approach that. Of course, if you're doing bulk diamond or if you're doing nano diamonds, we're not going to be able to flip and thin it away. So you'll just get the extra growth material on top of that nano diamond, which would then, have what you're looking for inside.
Yeah, thanks, Blake.
No problem. I'm happy to answer any questions about anything.
Answer your question, but
yep. I'm getting a question in.
Sorry, Santiago here. Thanks very much for the presentation. I was very impressed with the results you show about reactive ion etching and that low roughness. Can you elaborate on that and provide a bit more detail on the sample?
So was this the reactive ion etching or the ion beam etching?
The ion beam etching in that case. It was the 1 nanometer or 0.5 nanometer.
Okay, so that was with the silicon substrate. So this was actually the almost very first run that I did with this ion beam etcher. So it's all a temperature controlled stage with a compressed silicon wafer, which means that you're going to have no deconstruction of your capabilities across the center of the wafer. Of course, in this particular scan, there is a further out region of the actual scan went from -6 to +6. Once you start reaching the very edge of the substrate, then you're going to start running into a little bit more roughness, especially at the very edge where the clamp is actually holding down, as the measurement system doesn't discriminate for how the substrate was being sat in. So the way your large wafer will sit in there is the very outer rim, probably about 3 millimeters, I'd estimate, is clamped down, and the internal section is all etched. This was purely done with argon on the system, and it was so smooth and precise that when I took the sample out, I had worried that I hadn't actually etched it. So I did a couple of tests and I showed, yes, indeed, I definitely had, and this is the roughness of the sample, which came out to be approximately, it went from, so for context, this sample had 800 nanometers worth of a silicon dioxide layer on top. It was a native oxide wafer. And as you can see, we etched it down till it had a thickness of 366 ±5.
Okay, thanks. So this was on silicon, so it would be
silicon dioxide. It was one of the, when we first got the machine, this is a part of our acceptance tests. So they bragged to us that they could get less than 1 nanometer roughness, and I said, prove it. And they did a very good job.
Thank you.
No problem.
Yeah, on the next slide, Blake, was that a diamond? Like with the
This
silicon
one?
dioxide? Yeah, this one.
Yep, that's silicon dioxide, and the material that I etched is diamond. This is using a very low power oxygen etch onto the surface, which meant that the selectivity against the silicon dioxide was fantastic. So we've been in the process of developing nanofabrication techniques using HSQ as an only mask. So HSQ under EBL becomes SiO2, for those of you who aren't familiar with EBL processes. And so when you create that structure, we can then go down and create any sort of structure that's appropriate for HSQ. HSQ has approximately, depending on how good your SCM or your EBL system is, should be able to make structures of about 100 nanometers if it's your average day. I believe some of the best papers I've ever seen still barely breach the 50 nanometer area. But depending on your ability to fabricate, and that's specifically on top of diamond, by the way, where diamond is an insulative material where you get secondary electron exposure onto your EBL, which can give you a little bit of an edging effect to the base of your structure, which is why we had some imparted roughness on the side of our mask in the first place. But the etch was intended to lower the physical etching parameters while enhancing the chemical etching parameters. So it was a highly active ion with a fairly low acceleration, which basically still achieved some physical etching, which is why you're attributing it to smoothness. So basically the physical etching component would have worn away any resputted SiO2 from the etching process, but then the oxygen portion of the etch just did most of the work for us. So we had very little wear on our SiO2 mask and a good amount of etching on our diamond. So this was done all on a bulk single crystal diamond that we bought from Element 6.
Yeah, looks impressive.
Thank you. Oh, there's a chat bubble come up. It's me. Oh, yeah. All right, I'll pause and move it over to your question.
Thanks for your fantastic presentation, Blake, and it was definitely a good learning for me. I've got a very generic, non-technical question. Obviously, I could tap on your shoulders and ask you right away, but for the benefit of other listeners. So if someone want to plan and use your facility, in terms of lead times from start to getting an access to the facility, lead terms, paperwork, how does it work? Because I presume some of them might be external users. What sort of preparedness they need to have in terms of working out their timelines and so on?
All right. So the process of working in my lab comes down to, first we assess how long of an access you need. If you need to come in, run a sample one time, get the results you're after and leave, I'm just going to basically come up, hold your hand, take you to where you need to go, and we'll run the system together. All that you need to do is sign the external user paperwork, which gives us an understanding of who you are, what you're trying to do, and where I can track you down for when we go about the charging process. Afterwards, if you're intending on doing a long-term project, you'll sign all the same paperwork. In the first few times you come, I'll be again hand-holding you to make sure you know where you're going and where you come from. But during that time, I'll establish you as a subcontractor at the university and get you access to a contracting card, which will give you key card access to the university. In theory, assuming there's no issues and no problems that are unforeseen, you shouldn't have any real interference between an understanding and acceptance of the project and your ability to start working. For the most part, I've found that with users, many people will be in the discussion phase of the project for up to a month before they even come in. So I've got ample time to take care of any paperwork related processes for you. I've tried to minimize the paperwork down to less than 3 documents you'd need to sign, where only one of them is to do with ANFF and the other 2 are to do with access and the nice piece of paperwork that begs you not to do anything too nasty to anyone while you're here. So in that case, we're streamlining that process. I've already spoken to UTS's internal processes to make sure that is a system that I can get basically signed and accepted. There shouldn't be too much discourse regarding access after that point. Worst case scenario, I will continue to give you access myself.
Thanks, Blake.
All right, happy to hear anything from anyone else. I wonder what the time is. We still got about 10 minutes before we get to the end of the allotted time frame, so I'm happy to discuss any further point in any further direction you'd need to hear about.
Hi, Blake.
Hi.
Hi. So it's Jason from University of Sydney. I just got a question about the HSQ EBL patterning you mentioned earlier. Is that done at UTS or somewhere else?
Yep, I did it myself. So we do have an EBL system. I will forewarn you now, it's one, not ANFF, and two, nowhere near the quality of the ANFF-related systems that can be found at USyd. So I was on struggle street for a while trying to get our patterning process up to a standard sufficient to create up to 10 nanometer structures. A lot of the work that I did during my PhD was figuring out methods to make nanofabrication more accessible to people with less expensive equipment. So even the photonic crystals, I did workarounds to make sure that I could achieve the resolution required, even despite working on diamond that was freestanding. It was a lot of work to figure out how to get a freestanding wafer of 300 nanometer insulative material to achieve 10 nanometer resolution patterning. So that was my big pat on the back day. But it was done in-house. But if you're looking for AMP-related EBL systems, I recommend USyd, especially since you're right there. You guys have got everything. And our one goes through the problem of terminal booking like I'm sure USyd's one does as well. A lot of the work that you see from my patterning came from sessions I did myself at 2 o'clock in the morning.
Right, I see. Yeah, I actually look after the EBL system here at USyd, and I'm just very interested in the HSQ resist that you use. Is that a liquid base or a dry powder HSQ?
We buy it, and well, we've been through different phases. So as you probably know, HSQ is very hard to actually get. We began with a liquid that we actually got from a collaborator, but now we have a powdered version which we mix and create at the same time. We haven't had nearly as much success with HSQ with the post mix as per the pre-mix. If you guys manage to get yourself a big bottle of the pre-mix stuff, I would be very happy to come and use that as well. It is a difficult thing. It's actually been more difficult to get a good quality HSQ into the country than it was for me to get chlorine in my lab. So it's a bit of a nightmare. But once you get it, it is wonderful to work with. It is a one-stop point and play to get a mask, especially from my perspective of a diamond fabricator. The contrasting chemistries of silicon to diamond just make it an absolutely rip banger of a mask to use, especially for large structures. I did struggle to create the nanostructures that are required for the photonic crystals. I moved over to Caesar resist with a tungsten metal mask, which I then use contrasting chemistries of SF6 to etch the tungsten and oxygen to etch the diamond, which generated a tungsten oxide layer on top of the tungsten, which is basically impervious to any oxygen-based etching. So that's a really neat way as well of counteracting the charging problem, because it already has a metal layer that's already necessary for the fabrication process. HSQ, as good as it is, don't use it on insulating material, and don't use it when trying to achieve anything less than 50 nanometers. There are better materials for that. But I even looked at a paper yesterday where they actually created silicon dioxide waveguides just out of directly writing them out of HSQ with nanodiamonds just housed inside the HSQ to create integrated photonic circuits. So it's a powerful tool, but it is obnoxiously annoying to get into the country.
Right. Okay. All right. Thank you very much, Blake.
Not a problem.
Thank you.
See, team, I know stuff beyond the AMP as well. Feel free to ask anything. All right. I feel like that probably satisfies most participants. Should we wrap it up there? Give everyone an early mark for lunch?
Yeah, just probably reiterate.
All right. Well, thank you very much, everyone, for this whole process. It's been quite fun. I always enjoy giving presentations like this. Repeating again, on the screen right now in front of you as both our contact details, both the UTS and the ANFF. So you can either talk to me or Navin directly, and we'll be able to get in contact with anyone you need to well, specifically, you'll get in contact with me and I'll help you out. Well, thank you, everyone. That was very good fun. I think we'll end it all there. You all happy? Sound happy? All right. Cheers, everyone. Thank you so much.